in equity. And this was comprised of a Series A of around just under 100 million euros, and then a Series B of 1.5 billion, which put and actually a little bit more than that. I think it's 1.7 million then for the Series B. But that Series B was the largest equity raise in Europe last year, which is a huge achievement in itself, and I think something the industry really takes note of. It makes us the largest green project to date, and I think hopefully a little bit of a role model for other projects that are still to come. And yeah, when we finalized our equity, we were plastered across the billboards in Times Square in New York, which was pretty cool to see the recognition for that, and things are happening. And yeah, finally, I think a lot of people, what springs to a lot of people's mind when we're talking about green steel is we think about, this is going to be more money, this is going to be expensive, who's going to buy this? In order to raise this money, something we've had to do is we've had to prove to the banks that we can sell this. So we've actually pre-sold nearly half of all of our steel production already. And this was a massive milestone for the industry, because there was a demonstration that there was a willingness to pay a premium for green steel, because that was usually what the naysayers were saying. That's why the old steel companies, or the incumbents, they may have been a bit hesitant, because there was a reluctance. Will people pay more for this product? And we have shown there's a willingness to pay, and we're seeing the green premium at around 25% of the full price. And is it still on, please? Okay.
Yes,
okay, but so yeah, so in 3 years, that's already all we've accomplished, which is great. What I'm going to talk about then for the rest of this presentation is going into more depth of what I've just talked about. So number one, why do we need green steel? Number two, what is green steel? Number three, when are we going to see green steel on the market? And maybe we'll slip in a bit of a who as well, of who's going to be buying it. If you just double tap on the picture on the top, it'll come up, I think. That, yeah, if you double tap on that, if you click on that. Sorry, I'm having some technical issues in the room, trying to get it on the screen. There we go. Yeah. Great. So yeah, that was just a kind of high level introduction. But then starting off with the first W, the why. So yeah, so CO2 emissions from the EU steel industry is equivalent to, and you can see on the screen, total Nordic emissions. So that's the whole of Scandinavia, Iceland, Denmark, Sweden, Norway, Finland. All of those emissions just from the EU steel industry, all the flights leaving the EU, about half all the cars in the EU. So in terms of numbers, this is about 200 million tons a year just from the EU steel industry. And for perspective, Jamaican perspective, Jamaica's entire emissions per year is 6 million tons. So we're looking at 200 million tons versus 6. So this is a massive number. And yeah, we'll go into more global numbers. So zooming out from just the EU then. In terms of the world, we're looking at, as I mentioned, 7 to 9% of global CO2 emissions. And what does that mean? I mean, I looked up some numbers before from a survey on EU emissions over 2023. And I think it was 23, it might have been 22. But the numbers were saying that 8% of global CO2 emissions, that which is, as you see, 3.5 billion tons of CO2, that is about equivalent to the total emissions of South America, Central America, North America, excluding the US, the Caribbean, and Africa. So the whole of America and the Caribbean minus the USA and Africa. That is the same as the world steel industry, which is unbelievable. I think that, maybe perhaps more shows how the CO2 emissions are really more caused by the rich countries, but I think it does still illustrate, the magnitude of this industry. And so obviously we've got 5% of EU emissions, as you can see, and that's actually about 25% of industrial emissions. Other big tickets are things like concrete, for what do you call it? Ammonia production for fertilizers as well as a big one. I think that's probably lumped together in industrial. And then for Sweden, it's 14% of the total emissions. So these are, yeah, massive numbers. And I think a big thing to point out here is just if you look at the ratio between tons of steel made and CO2 emissions. So what you can see there is it's around a times 2 ratio. So for every ton of steel we're making, you make about 2 tons of CO2, which is a huge amount. So to give you some perspective on that, is that what we're getting into? Yeah, so to give you some perspective on the 2 tons of CO2 per ton of steel. I think a ton of CO2 is quite a hard thing to wrap one's head around. It's not a number that's tangible. If you turn that into meters cubed, so obviously CO2 is a gas, so the volume of that CO2 taken up, that works out to about, so, you know, for 1 meter cubed of steel, so kind of a steel lump like this, you know, we're going to see about half an Olympic swimming pool's worth of CO2. So that's about 1,100 meters cubed of CO2. So that just gives you perspective on kind of how much we're making. Yeah, so then getting into green steel, who are we? So this is our kind of mission statement, our purpose. We decarbonize hard-to-abate industries, and we start with steel. So I think, what is a hard-to-abate industry? Those who aren't in the industry may not, you know, recognize that terminology. A hard-to-abate industry is an industry where CO2 production is kind of integral to the process. So it's not easy to switch it out. So for like heating, you know, things, so like burning natural gas, obviously that's you know, emitting CO2, but that's not a hard-to-abate, you know, process, because you can just switch that out for electrifying it, or, you know, burning, you know, green natural gas, you know, biogas or something like that, and then you're immediately removing the CO2. Hard-to-abate industries are industries where the CO2 is produced by the process itself. So in the case of steelmaking, like I mentioned, it's not that the CO2 is emitted from burning something, it's the chemical reaction that's going on in the process, so the reduction process. Therefore, you need to find a new reducing agent, which makes it a lot more complicated than just switching out something that is used for heating. So that's our mission statement. I think, you know, and we're starting with steel. We really have, you know, eyes to the sky here. We've got large targets. We really want to try and, you know, we're focusing on steel right now, as we see that's kind of the low-hanging fruit, something that's easy to, well, you know, there's a lot of CO2 emission reduction that we can see there. You know, the technology is mature, but, you know, in future, you know, we can see us expanding into other industries potentially, including, you know, maybe ammonia decarbonisation. And also, Sweden is just a start. As I'll talk about later on, we're looking at expanding into other countries, especially where the geography kind of suits decarbonisation of steel. So yeah, so who are we? So as I mentioned, we're situated pretty far north. So I may have only lived here for 4 years, but I definitely still enjoy the warmth. And up there is pretty cold. I think over the winter we hit around -40 up there. So that's extreme. Normally it's more around -20 or -30. But as you can see, it's up in the north of Sweden towards the tip of the Baltic. It's a town called Boden. And we're just outside that town. We're going to be building our factory. We've also got an office in Stockholm, which is where I'm based. But yeah, the plant itself is, you know, we're going to be producing 2.5 million tons of green steel every year. And to do this, we're going to have an 800 megawatts or thereabouts electrolyzer producing hydrogen, which is then, you know, producing the green iron and subsequently the green steel. And as I mentioned before, our steel will have 90 or 95% less emissions per ton of, 95 to 95% less emissions. So that means, you know, we were saying before, it's 2 tons of CO2 normally per ton of steel. Ours will be more like 0.2 or less tons of CO2 per ton of steel. So it's a huge change. And that's just really the beginning. That's the end of 2025 plan. Well, that's phase 1. We're then going to be expanding this into a phase 2, where we're doubling production into 5 million tons. And that's estimated around 2030. And obviously, you know, the close customer partnerships, this wouldn't be possible without that. So yeah, so now I'm going to kind of, we've got a room full of engineers, physicists. We're going to go a little bit more into the process and try and, you know, understand exactly what is the difference. I keep saying green steel, but I think it's helpful to talk about, you know, how this differs. So starting off with the traditional process. So this is, you know, steel, as I mentioned, steel has been made for thousands of years because it's very easy to produce iron from iron ore, and then you get, so iron is the most abundant element on Earth. It's in the form of iron oxide. You put in some carbon with the iron ore and you heat it up, and you immediately get a spontaneous reaction where the carbon, as I mentioned, is binding to the oxygen in the iron ore and taking it out. So you can think of the carbon as more reactive than the iron. So it'll steal, because it likes the oxygen more, it'll steal the oxygen off the iron oxide and form CO2 and pure iron. So as this is what's called a exothermic reaction, which means it generates energy in the process. So that means that it's heating up as it's going, which means, you know, in terms of kinetics, that's kind of pushing the reaction even further forward because you're generating energy as you're going and it's heating up and you need hot iron anyway. So that's why it's been made for thousands of years. You can find a lump of coal somewhere, you can find some iron ore somewhere, stick it together, you know, burn it a bit and it just goes. And that's why we have swords and all these kind of things thousands of years ago. So the current process is really no different from that, but just on an industrial scale. You start off with coal. You put that in a coke oven. That coke oven purifies the coal and powderizes it into what's called coke, which is just very high purity carbon, basically carbon powder. That then goes into a BF or blast furnace. This is a giant furnace, and you throw into that the iron ore that you've dug up out of the ground and your coke. So your iron ore is mixing with the carbon. You heat it up. They react, you're forming huge amounts of CO2, and out the other end, you're also getting carbon. So you're getting pure iron. So this is generating, you know, lots of CO2 emissions in the pure iron. So out the other end, you get what's called pig iron. So this isn't steel yet. So this actually, not all of the carbon you put in is used in the reduction and is turned into CO2. A lot of that actually gets integrated into the iron lattice. So what you end up with is iron with a very high concentration of carbon relative to steel. So this pig iron has around 4% carbon, whereas steel that you're using in your car and all of these things, that's more like 0.1% carbon. So it's a lot more carbon. So you're then with a product or you call it a virgin iron product because it's new iron that you've just made. You then have a virgin iron product with too much carbon. So then you put it into the next step, which is the basic oxygen furnace, the BOF. And then the goal is to remove that carbon because you've got too much carbon now. So you have even more CO2 emissions because how do you remove the carbon? You blow in a load of oxygen. And if you're blowing in lots of oxygen, that's binding with the excess carbon, generating even more heat, melting it, which is what you want because you start with a molten steel, you cast it and, you know, turn it into whatever you want to make it into. So you blow in oxygen, blows out all the carbon and melts the steel. So you've got both of these steps, you're generating huge amounts of emissions. So then you have a molten steel, which is ready for casting and turning into whatever you want. In our case, what we do is we make flat products. So we pour it into a big slab. We then roll that slab out into very thin sheets and then roll it up like a toilet roll, basically. So that's what you're seeing here. It's the kind of toilet roll flat products. So in that whole process and downstream, you need to keep it hot while you're rolling it, so it's malleable, etc. And there's also some, you know, annealing furnaces. It goes through different furnaces to change the properties of the product. This means that to do all that heating, you're also using energy, and typically you're using natural gas. So you're also making CO2 emissions there. So, you know, we're having CO2 emissions in every step of this process, and that's what really gets us to that 2 tons of CO2 per ton of steel. You can't see on the screen, but it says 2 tons behind my face. There you go. Yeah. So that's the background. So that's why there's so many emissions. So what are we doing differently? So looking at it step by step, the first step is generating the reducing agent, right? So the reducing agent, as I mentioned, is the thing that steals the oxygen off the iron oxide and leaves pure iron. So traditionally you use carbon, which is stealing the oxygen. In our case, we're using hydrogen. So how do you make hydrogen? Traditionally in industry, you make hydrogen in a process called steam reforming of methane. So you're taking methane, natural gas, and you're breaking it down in the presence of water into natural gas components. So carbon dioxide and hydrogen. So that is a traditional way. If we were to make our hydrogen in that process, all we'd be doing is shifting the CO2 emissions to a different step. So we'd just be making more CO2 emissions further upstream. So it doesn't make any sense. So we can't use that process. So instead we use a process called electrolysis. Electrolysis is not a new technology at large scale. You know, electrolysis was actually the preferred method of generating hydrogen, you know, in the mid to early 20th century. It became less popular when the prices for natural gas fell from the floor, and then it became more economical to generate natural gas through steam reforming of methane. So this is not a new technology, but how does it work? So the process is you put in water, H2O, and you split it up into its elemental constituents. So you split up H2O into hydrogen and oxygen. And so you're generating hydrogen and oxygen. You do this with a lot of electricity. So you can think of it as water molecules are polar, they've got a positive side and a negative side. The negative side is the oxygen, positive side is the oxygen. You put it in a giant electric field and it'll rip apart the molecule, and hydrogen will be generated at one side and oxygen will be generated at the other. This isn't exactly how it works, but it's a good analogy, and that's basically it. So you put in electricity and you're producing hydrogen. There's a few different technologies for doing this. The most mature technology is a technology called alkaline water electrolysis. This is, this is the technology that has been around for, getting on for, 80 plus years. It draws a lot of learnings from the chloroalkali industry. So the process industrially for generating chlorine gas is also an alkaline electrolysis process. So there's a lot of learnings from that. And yeah, because it's been around for so long, there's been a lot of improvements. We, as a kind of new company, there are newer technologies out there, but we need to have the most reliable of these technologies. We can't be taking a technology that's straight out of the lab and putting it into industrial scale. So this is really seen as the most, I use the word bankable, so, banks willing to finance it, technology. On top of that, it's actually lowest in cost right now in our view. So cost of hydrogen is evaluated in terms of what's called LCOH, levelized cost of hydrogen, so the kind of euros per kilogram of hydrogen, as well as being the most mature. We see AWE, alkaline water electrolysis, as the cheapest option. So that's why we're going down that route. But in future, in phase 2 of the project and onwards, we're looking to introduce some of the more novel technology, such as PEM, so that's proton exchange membrane electrolysis, and SOEC, so solid oxide electrolysis. So SOEC particularly, I won't go into depth in it, but that's really seen as the future for electrolysis and a way to make your process way more efficient, by which I mean you use less electrical energy per unit of hydrogen you generate. So yeah, so we're using electricity to generate hydrogen. And just a quick note on the electricity, which is a critical point really, is again, if we were using electrolysis, but we were getting our electricity from a coal power plant, again, all we're doing is moving our CO2 emissions to a different step in the process, because then all the CO2 emissions are being emitted from the process of generating the electricity in the first place. So you need a green source of electricity to make green hydrogen and decarbonize the entire process. So green sources of electricity, obviously there is wind, solar, and so on. But the main one which we're really going to be using up in Bowden is hydroelectric power. I think one of the big benefits of hydroelectric power is how it is continuous. I think with wind and solar, you have the issue of its temperamentality. So you don't want to be, you can't be paying 5 billion euros for a steel plant and then only operate it during the day because it's sunny then. You need to be running these pieces of equipment 24/7. These things are basically on all the time. And so when you're looking with wind and solar, to compensate for that, what you end up having to do is, either have massive batteries to, store electricity during the time when, it's producing and then use it when you're not producing, or have some sort of hydrogen storage, which is, storing hydrogen away for when you're not producing hydrogen. So it makes it a lot more complicated. It's not impossible, but I'm just saying it's more complicated and it's more capital intensive. So we're using hydroelectric power. So then we have this, so that's the reducing agent, that's the thing that's removing the oxygen. This is then going into our DRI plant. So that stands for direct reduced iron plant. This is where we're generating the green iron. So this is where that hydrogen is being used. So that is then being, you're putting in your iron ore at the top. This is actually, you see a model of our plant. This is kind of the key landmark. This DRI plant is about 150 meters tall. So it kind of sticks out and it's going to be red. So you're definitely going to notice it. Good question.
Just to recap, I'm saying you're going to use green energy to get green steel, so to speak. You're not using hydrogen plants to create green steel. So I'm just thinking that it's going to be a lot of water involved.
Water, yeah.
Massive amount.
Yeah.
You need it for the plant side and you also need it.
Exactly, yeah. No, there are large amounts of water involved. It is not on the order of magnitude that is unheard of in the industry at all. It is, as you mentioned, the steel plant itself consumes a lot of water. We also, are very wary about our water emissions. We're actually going to have a zero liquid discharge system for our water purification system, which basically means we're not going to be letting out any wastewater into the environment. Yeah, and reusing it exactly. But yeah, it's a good point. We use a lot of water, but there's a lot of water up in the north. I mean, all of those there's a lot of hydroelectric power up in the north. That's because there's a lot of rivers, and there's also a lot of water in those rivers. But to be able to get the environmental permits, etc., for the project, we have to be very clear with the municipality about how much water we're going to be consuming to ensure that's not damaging the environment, going beyond what the limit is that is feasible. But no, thank you. But then moving on to the DRI. So the DRI plant, as I mentioned, that's where you're making the iron, 150 meters tall. It's a big tower, basically a big reactor. Your iron ore goes in at the top, and it's a continuous process. It trickles down in the column, and at the bottom you get a constant stream of DRI. So this direct reduced iron. So what's happening in the column is your hydrogen is being fired into the column. It's being heated to around 900 degrees C. It's reacting with the iron ore, and it's removing the oxygen. And then at the top, you have a mixture of gases, and a lot of steam really generated, because obviously there's water being generated in the process. So your hydrogen is binding with the oxygen. I think something to mention is the fact that you have to heat that hydrogen. I said before that it's a really easy process with carbon. You just kind of react the carbon with the iron oxide, and it goes, because carbon is more reactive than the iron. It's an exothermic reaction. The converse is true with hydrogen. You need to put energy in to make it go. So you have to heat that hydrogen to make it want to steal the oxygen. So we do that, and we're using an electrical heater. So obviously, we don't want to be using a natural gas heater, create more emissions. Also at the top, we're going to be, there's going to be some unreacted hydrogen. So we have a special system called a pressure swing absorption system, a PSA, which is going to recapture any unreacted hydrogen and recirculate it. So we're not just blowing it up into the atmosphere and wasting that. Another point is, you may hear me talking about decarbonising throughout this entire presentation, but at the end of the day, steel is still iron and carbon. So you need to add carbon somewhere in the process. You can either add it here, so when you're making the iron, or the next step when you're making the steel. And we see it as more efficient in terms of units of carbon absorbed into the steel versus emitted at this step. So we're going to be adding carbon here. So we have a small stream of natural gas going into this, which is going to add carbon to that DRI. I think, just to note on DRI plants, this is not new technology. This will be the first large-scale DRI plant using only hydrogen, and it's been planned for only hydrogen. But DRI plants conventionally, they've been around for 50 plus years, they run on natural gas. So you have natural gas coming in just before they go into the column. They have to do steam reforming on the natural gas. So you split it up into carbon monoxide and hydrogen, and then you put those into the column. And the hydrogen going in is actually doing 60% of the reduction normally. The remaining 40% is done by the carbon monoxide. So all we're really doing is taking that pre-existing technology and cranking it up from 60% hydrogen to 100% hydrogen. So I think that's another point of demonstration, the maturity of this project. It's not like we're taking something from lab scale. This has also been proved on pre-existing DRI plants, which haven't been optimized for hydrogen, but they've been shown for a couple of days to run on hydrogen. And we now have a pilot facility up in the north of Sweden, not ours, but a partner of ours or a collaborator of ours, Hybrids, who has shown at pilot scale that this can be done. But the DRI plant itself is going to be supplied by the leading supplier, the incumbent of DRI plants worldwide. So as you do with any large equipment contracts, in buying this, they also have a number of different guarantees, performance guarantees, to bring confidence that they believe that this will work. And if they don't meet those, there's obviously penalties for those. So for them to feel confident enough to be able to offer this technology, a company of this size and accreditation, it's a demonstration of the maturity of it. Not to mention all the due diligence that all the banks have done on it. But this is really the area of novelty then. This is the key point. No one's done this before at large scale. I think in terms of another point of novelty, so the electrolysis facility, electrolysers haven't been shown on the scale that we're going to be using. So I mentioned we're going to be using 700 or 800 megawatts of electrolyzer. For scale, that's like a whole large hydroelectric dam. That's a lot of power, and that's only about half of the whole plant. I mean, this is huge amounts of power. Electrolyzers are modular though. So they're like batteries. There's just lots of them lined up. So in terms of de-risking, you know, it's just a case of adding more to an existing technology. So having, you know, a couple more rows rather than just, you know, one or two. So I think that's another point in terms of scaling the technology. In terms of, yeah, I didn't actually mention this. So how much hydrogen is a DRI plant consuming? It's consuming around 12 tons of hydrogen every hour. So that's around, you know, 56 Olympic swimming pools of hydrogen. I like to use those as a kind of metric, more tangible. So there's a lot. And out the other end, we're getting 260 tons of iron every hour, which works out to about 2.1 million tons a year. So what's happening with this iron? This iron is then being turned into steel. And we do this in the EAF. So that stands for electric arc furnace. So again, this is not new technology. This is the basis of the technology that you see in a lot of the US steel mills. So it's called the mini mill concept, where they just have these big furnaces, basically, which can melt scrap and virgin iron. And by virgin iron, that could be pig iron from a blast furnace, or it could be DRI from a kind of a green process with either natural gas or hydrogen. So we're obviously going to be using the green DRI. We're going to be mixing that with scrap metal that we get, and we're going to be producing, you know, from that molten steel. Basically, you have the furnace. We are going to have two massive melting pots. Effectively, you put in a mixture of scrap and DRI, you melt it, and then you pour it out and cast it. In terms of energy efficiency, we're going to be transporting the DRI directly into the EAF while it's still hot. So we're not losing any of that energy. So it's going to be going into the furnace at like 600 degrees C. So we're still keeping that energy. So I think, yeah, so that's the melting, and that's all electrified. The heating is done with an electric arc. So again, you're just using energy. In terms of the downstream, as I mentioned before, there's a lot of natural gas consumption in the traditional process. We're going to be instead electrifying those processes to make it entirely decarbonized. Of course, we aren't 100% reducing all the emissions. We're saying we're reducing emissions by 90 to 95%. There's still some places that we need either to burn natural gas, or, for example, we're using natural gas in the DRI plant. And there's, you know, that's not perfect. There's some CO2 that's emitted. Yeah, so we're working to, we have, you know, a target of, you know, decreasing that further with time, but, you know, 90 to 95% is definitely a good start, we'd say. So with all of this, you get to the kind of less than 0.2 tons of CO2 per ton of steel. Yeah, so that's the picture, that's the process. And yeah, some more kind of headlines just to kind of skim through. You know, as I mentioned, this is going to be powered by one of the largest electrolyzers in the world, or the largest projects to date. It won't be the largest, I don't think, but it'll definitely be one of the largest when built. What else have we got in here? You know, just some points on power. You know, power for this is obviously critical. You know, this is, you know, talking about the grid connection that we're going to have to be able to kind of supply this amount of power, and how we're working with the municipality there. We also have one of Europe's largest deep water ports very nearby, which is Luleå Port at the north of the Baltic. So that's going to be where we're getting a lot of our different products, also different inputs. And yeah, of course, world leading expertise from all over the world, very international, not just Swedes by any measure. You know, a lot of Americans, Indians, South Africans, people who have a lot of experience on large projects, and people who have experience in steel mills. Yeah, a little bit on our timeline, just to show you, you know, how, as I mentioned at the beginning, you know, we started out Q2 2021 with our Series A, and it's just been, you know, absolutely rocketing through and trying to make as much progress as possible, because it is a bit of a race to who can produce the green steel the fastest. If you looked at the timeline when we started the planned green steel project, there was basically nothing, like maybe one in, you know, 2040 or 2035. Since we've started and we've proved that this is something that is doable, the willingness to pay on the market, there is now a plethora of different, you know, companies that are going to be offering green steel over the next 10 years. We're still currently believe we'll be the first to produce green steel, but you know, we've got to move fast to be able to hold that title. But it's, you know, aside from that, it's, you know, it's great to see that, you know, even if nothing were to work, we have really, you know, as well as others, you know, catalyze change in the industry, and, you know, force the kind of big players to really accelerate their timelines. So yeah, so this is the overall timeline. That's the plant, you know, 3D render. So this is I'll use my mouse so people can see online. So this is the substation that's already there. Actually, there's going to be another one built. This is the hydrogen facility. We're going to be generating hydrogen here. Hydrogen is going to be piped over here to this tower. So this is the 150-meter tall DRI tower. This is where we're producing the green iron. And out of the green iron, we then go over here, which is over here is the steel mill. We're going to be making our steel, and then there's lots of different downstream finishing lines where you're refining that steel product into slightly different types of products. So that's what it's going to look like in 2020, end of 25, 26. What else have we got? Yeah, so no customers. Obviously, this wouldn't be possible without the customers. We had to show the banks there was a willingness to pay this premium, that people were going to buy our product. As I said, we already pre-sold around 1 million tons of the 2.5 million tons per year. These are some of our customers. I mean, who's willing to pay this premium? We're selling to a lot of automotive. So you can see on here, BMW, Mercedes, Scania, Volvo. This is obviously going into their EVs, their electric vehicles, helping decarbonize there. But also a lot of construction as well. So that could be like insulated paneling. We've got Kingspan on there, and then white goods. So things like washing machines, dishwashers, hobs, these kinds of things. But and also to re-rollers, so people who take our steel product and further refine it. So there's a massive variety of different customers in here, and we're actually kind of putting on the brakes at 1 million tons a little bit, because we don't want to oversell. So we really see this premium also increasing in the future, because right now we're seeing huge demand and a lack of supply. So we see that premium that we could get is only increasing later on. So it's actually in our favor to hold out a little bit at this point. In terms of investors for the series A and B, we've got, again, a massive range. Some of them being customers that you saw on the last page, some of them being suppliers, and people, supplying equipment. You'll see like SMS Group on there, which is, who's providing our steel mill. But also, some, people with a lot of weight in the financial industry. So, for example, Altor, same founders of a company called Northvolt, which is they were our original founders. So Northvolt is a giant battery manufacturing company in the north of Sweden, and one of the biggest in Europe now. We've also got Just Climate, which is Al Gore's impact investment funds for decarbonising. So big name there. We've also got one of Sweden's largest pension funds, just to demonstrate the risk of this kind of project. The fact that they're willing to invest in this, I think, shows the confidence and the level we are at this project. This is a sort of pension fund that everyone is practically by default, their pensions, are somewhere in. So, this is, I think it shows that the risk level here. Yeah, as I mentioned, debt, 3.5 billion from the leading European financial institutions. Just some more headlines, 5 million tons, jobs, of course, there's going to be a lot of jobs generated up in Boden, which is great. Encouraging, people up to the north and growing the northern industry. For the DRI plant, as I said, we're partnering with Midrex. For the steel plant, SMS Group, and for the electrolyzer, ThyssenKrupp Nucera. And yeah, this, as I said, this is just the start. We really see this as kind of the mothership. We always, our CEO calls it Boden, but we kind of want to, now we've created this kind of repeating unit of how you can build a green steel plant. We want to use that knowledge to build steel plants or green DRI production facilities elsewhere in the world. So there's we've got to look for favorable geographies where this is possible. And we're already looking at a project in the Iberian Peninsula with Iberdrola. This is for DRI production. We'd be partnering with Iberdrola here. But this is we're also looking elsewhere. I think the Americas is obviously really interesting. I think it's great. This is a demonstration that it can be done with not just hydro. We're looking at wind and solar. But yeah, obviously we're looking elsewhere with lots of wind and solar, lots of hydro in the world, and yeah, we'll see what happens. But the focus obviously right now is making sure that we get Boden, get it right, and so that's what we've been working on the most. But yeah, also in terms of funding, something I didn't mention is so we also have been selected for funding from the EU Innovation Fund. We have a lot of different public funding been selected for lots of different public funding, but the EU Innovation Fund is a really, it's a massive achievement to be able to be selected for one of the funding given by the EU on that. I mean, that could be up to 250 million euros just from them. They're currently working out the exact sum they're going to be giving all of the different winners of the prize this year. But I think that's a really, really important point. Yeah, and also a magnitude. So one last point. So we're going to be making 2.5 million tons of steel. That's about an Eiffel Tower's worth of steel every day, which I think is a nice number for you to kind of think about. The magnitude of the steel industry is totally crazy. But yeah, that's all I have to present. And I think I was around 45 minutes, maybe 40. Thank you.
So if it's online, you can type your question in the chat or use the raise hand feature and we'll give you the floor.
Two quick questions. We keep talking about premium pricing. What percentage of the premium pricing
So the price that we've been achieving right now, we're seeing in the market is around 25%, but we're seeing it as having potential to grow beyond that. But that's what was being proven right now.
The second question was, what's the total? What percentage of the world manufacturing of steel is done?
So it is. Yeah. So I think it is. Oh, I think can I write that down? I think total steel. Yeah, actually, I have the numbers. Total steel production is 2 billion tons a year, and we're going to be 2.5 million tons. So do the math. It's 2 billion total. 2 billion total, and then if you yeah, exactly 1.9 billion to 2, and we're producing 2.5 million phase 1 or 5 million phase 2. And we should also mention that we're focusing on flat products. The steel industry, so that 2 billion also comprises of making steel plates, making steel bars. This is just flat products we're looking at. Thank you. Do we have any others?
You said that there are some other initiatives globally to do the same kind of green steel.
Yes.
Well, if you know, because there's 9 laws to it, right? How does what they are doing differ from what you are doing? Is there anything?
So no, as I mentioned, we're not inventing any of this technology. This technology exists.
Right.
So others can go and purchase a steel mill from SMS, purchase a DRI part from Midorex, and hydrogen from ThyssenKrupp and stick it together. So no, there is no kind of innovation on our side in terms of the technology being, well, we'll be the first using it, but we're not making that. Others can go away and do that. I think the challenge is a little bit, finding a place for the correct geographies. Obviously, to make it cost effective, you need to be somewhere where there's a lot of green energy and it's at a relatively low price. We're really dependent on energy prices. If you're making, green hydrogen in Central Europe, it's going to be a challenge because prices are much higher. So the other projects out there, there are, not as many that are going the whole hog. So starting off with hydrogen, a lot of those in Central Europe, they have a DRI plant planned, where the DRI plant is maybe starting off with natural gas and then going to hydrogen. So that's obviously a massive step in the right direction. The emissions from a natural gas DRI plant is a lot less than a blast furnace, which is what I was describing before. So that's in the right direction, but it's not quite, the full hydrogen model. There are hydrogen plants, hydrogen versions also planned, some in the Middle East, also some in Sweden, so SSAB and LKAB, we've got working towards that. I think their start production is going to be more towards the end of the decade, so more towards 2030. But there are a few out there. I think often the DRI can then be put into existing steel mills, so you don't need a whole new steel mill. You can put it into an existing process to help decarbonize the value chain. But yeah, that was kind of a long-winded answer.
No, because the other part of my question was the replicability elsewhere.
Yeah.
Clearly, from what you have set up in the very beginning, the location was critical because you have to have the hydro to reach the 95%. But based on your last answer, my assumption is somebody could set it up by moving the DRI into an existing mill. They may achieve, I don't know, a smaller percentage, but they will also be moving towards the decarbonization.
Absolutely, and I think it's important to note that we sometimes see the repeating unit isn't necessarily building another green steel plant. It could just be building the hydrogen facility and the DRI plant, and then they're putting that into existing facilities. You know, so much so that in our phase one, 2.5 million tons, we won't actually be using all of that DRI.
Oh,
So what we're not using, we'll be selling to the market to help decarbonize other steel mills.
we have 2 questions on that. So
Which one's number one?
that's the first.
While production. Are there any other Of course, I mean, like, it is still a steel plant. It is green relative to traditional steel, but it is, you know, still very much an industrial process. So I think an unfortunate number is, you know, we're going to be using a relatively minuscule amount of natural gas to carburize our iron to make steel. But that will still make us one of the largest natural gas consumers in Sweden. But that isn't really because, you know, that is because just of the scale of the project, right? So there will be impact, but I think, you know, it's important to look at it in terms of an alternative. You know, if for every unit of green steel that is sold instead of brown steel, then there is a huge decrease in CO2 emissions. And in terms of ecosystem and biodiversity, obviously to build this plant in the north of Sweden, Sweden has very strict environmental permit laws. So we had to apply and receive the environmental permit before we could, you know, really go headlong into the project, which we have now. We managed to do that in absolutely record time. And given the strictness of the courts up there, I think that is a demonstration of the, you know, as they see it, the positives really outweighing the struggle here. So yeah, and actually one point on that, which I always like to say, and I forgot to mention it, is just a bit of a number to give you an idea of, you know, how decarbonizing it is again. Is normal steel, 2 tons of CO2 per ton of steel, our steel about 0.2 tons of CO2 per steel. So the difference is 1.8 tons of CO2 per ton of steel. The amount of, so woods, trees, they capture CO2, right? And they turn it into wood. The amount of CO2 captured in a ton of wood is actually conveniently 1.8 tons. So in making 2.5 million tons of steel, it's kind of like, in terms of CO2 capturing or, you know, lack of emissions, it's kind of like producing 2.5 million tons of trees. So that's kind of one way that I like to think about it. But yeah, maybe a bit, you know, not 100% good, but in terms of lifespan, did I answer whoever's question that was? I hope that was okay.
Thank you. Yes.
Great. In terms of lifespan of this green steel, how does it compare with original steel? So yeah, maybe I didn't go into enough detail there. The steel is exactly the same as normal steel. It is exactly the same. We're just using a slightly different process to make it. So instead of making the iron with carbon, we're making it with hydrogen. So the actual product you get is identical. There is no difference. So it's, you know, you can use it anywhere. It's just there's less emissions in the process.
Can you speak to the quality of iron that needs to be there? The same things that you use.
Sure, yeah. So the quality of iron ore, so DRI processes require higher quality iron ore than blast furnaces generally, and that is something that is part of DRI. Shireen,
Take some time. I can show you the list. Just say that yes, it says that she has been seconded.
Where that goes.
oh, maybe I don't know.
Shireen, you may be unmuted. Not Shireen. Go ahead.
Yeah, so DRI plants slightly more
All right, when this is finished, I will check the list.
than
Yeah.
but we, you know, as I said, DRI plants have been around for 50 odd years now.
The internet not going to come through because I'm using it. So you just wait a bit, okay? The meeting will finish.
So there is, you can go ahead, forgive us.
So when you say higher quality ore, what does that mean?
Yeah, so it means a higher percentage of iron in the iron. So what you have to do is The iron you dig up out of the ground is like, lump iron ore, you then, or powder usually, so fines. You then need to kind of refine that. So it's in a process called beneficiation, where you're basically increasing the purity of the iron ore. And then you go into a process called pelletizing, where you turn it into a little pellet, so a little ball like this, and that's what goes into DRI plants. But that's the same for all DRI plants, not just ours. Of course, it comes at a bit of a premium having high quality iron ore, because obviously you then have like less losses and all these kinds of things. But there is large production globally of iron ore pellets. I think as more people shift to this way of steelmaking and the number of DRI plants proliferate, there is going to need to be an increase as well in the production of high quality iron ore. But as I said before, it's a case of purifying the iron ore. So the iron ore is there. It's just you need to maybe have more beneficiation processes and more pelletizing processes as we shift from blast furnaces more towards DRI. But
The assumption is that that process does not take any carbon into account.
yeah, no, but that's a great point. I mean, there are CO2 emissions in that step, absolutely, in the pelletization process in turning into a pellet. But they are nowhere near as much as what's in happens in the blast furnace. So I don't have the numbers off the top of my head. Net in terms of from iron, what is the difference in CO2 emissions? But another point is we don't have the coke furnace that I mentioned at the beginning, which is also generating CO2. But I don't have the numbers, from all the way from the beginning of the value chain, but it is still much less CO2 emissions.
Green building has been known now, the different systems and material with different credits for the certification. Does this green steel add to that?
For green buildings.
The green buildings, as we know now, they have different systems, whether electrical system, system for water supply, or the material that is used in the building. It's certain credits toward the certification.
Okay.
Are there any consideration where using green steel would add to that credit?
So I'm not sure how the accreditation process works.
It's mostly about
Okay, well, I'm not sure, but I imagine it is calculated based on the CO2 emissions of all the product or the consumables used in the process. In which case, it would have a massive impact. I imagine steel is relative to other things that decarbonizing is a huge emitter. I think this whole project was fostered out of talking with people in the automotive industry and saying, what do you guys need? And they were saying, well, if we want to meet any of our targets, we need green steel, because basically all of our emissions come from steel. So I think that shows that in these kind of, electronics buildings, whatever, a huge portion of the emissions comes from steel. So yeah, I definitely believe that you would definitely get credits. And yeah, like in terms of credit systems in Europe, we're seeing EU ETS. I don't know if anyone has heard of this, but that's the energy trading system. So, people are going to have to start soon paying for every ton of CO2 that's in the product. So yeah, people are more and more starting to, monitor these carbon tons and, having to pay for the extra CO2 they're emitting. So I'm sure, but I don't know.
Just curious about you mentioned 3 different types of the furnaces. Individually, if you consider BF and BYF and EF, which one contributes to more emissions?
What's the hard question? So the EAF is what we're using. That's the alternative to the BOF. The BF, the blast furnace, that's really the alternative to the DRI plant. So if we go back to this slide. So you use the BF and the BOF in conjunction, they come together. So in terms of, so the EAF is obviously the least emissions, assuming you're using green energy, but even if you're not using green energy, it's the least emission. Because you're just putting in electricity, basically green electricity. The BF and the BOF, you're making huge amounts of emissions. In the BF, that's because you're putting in all of the carbon to do the reducing of the iron ore. In the BOF, that's because you're blowing out the excess carbon that was in the iron ore. So in the iron that's coming out of the BF, the pig iron. In terms of which has the, I'm not sure of which has more, blast furnace or basic oxygen furnace. It's a good question. Not sure, sorry. I'll have to come back to you on that one. But you have to use them together is the point. So I think looking at them individually isn't as relevant because we need to look at the full kind of from iron to steel products. You never just have, well, you could just have a blast furnace, I guess, and then take the pig iron and put it somewhere. But generally, steel mills have the full downstream. But yeah, so BF and BOF far more than the EAF, which is why we have the EAF, because we're using green electricity.
Is there waste produced from steel?
Absolutely. So in the DRI plant, we generate some fines, some dust. So not in the DRI plant, there's no slag. It's just iron ore dust. Slag is generated in the EAF when we're making the steel. And just like in normal steel making, you're generating a lot of slag. So EAF slag is a bit different to blast furnace slag, but it's very common. As I said, there's a lot of EAFs in the US. So we still have, significant slag generation. So we're going to have slag processing plants on site as well. And we're looking to, how we can, use these and, go towards circular economy. So using the slag in, as concrete or something like that to help, further decarbonize the whole picture. So again, because of the strict permit requirements in northern Sweden, we have to use it. We can't store it on site. A lot of big steel mills, they just kind of put it in a hole and forget about it. We can't do that. So we're looking for people to, offtakes for it as well.
If you look at the percentage of total steel production that this plant is making worldwide, it's like about to meet any demand, when you have to multiply this by about 1,000 times.
Yeah.
Whereas a hydroelectric power plant come from.
Yeah.
Hydroelectric power plant takes a lot more money to build than this.
Yeah.
And a lot more years to
Yeah.
build. And you might not even have the water capacity or not, the river capacity or not.
I mean, absolutely. To be able to change every steel mill in the world for this, I mean, that is a process that would take 100 years, maybe. I mean, and the amount of capital that's invested. So I agree. It's there's not you need way more hydro, you need way more solar, you need way more wind. But it is a slow process, and it's about steps. And sure, maybe in 30 years. The most bankable and the most feasible and most economical way of making greens product will no longer be this way. But today, this is the way, and it is, a very efficient way of using green energy units to help decarbonize an industry, which is, very emissive. You can think of green iron, so the thing coming out of the DRI plant, as like a unit of green energy in a way. It's a way of, turning that green energy and putting it into an industry which otherwise isn't benefiting from the decarbonization of energy. So it's like a green unit. But yeah, I agree, we're not going to see China change all of their blast furnaces for these anytime soon, but maybe they'll start doing, using EAFs and buying, a little bit of green DRI from abroad, and then it's, baby steps.
But in your process, if you took out the green electricity,
yeah,
and replaced it with, I don't know, whatever it's that.
Well,
you use something current. What would be the percentage reduction?
So the amount of CO, so as in if we were to have a normal DRI plant, which is on natural gas instead of hydrogen, the emissions per ton, I can't remember. You are seeing it is a lot less than 2 tons.
It's still a lot less than 2.
It is a lot less than 2 tons. I think it's more like, it may be like maybe 0.8 tons or something, or a bit more than that, maybe. I'm not sure, but that's with the natural gas. So that's what a lot of mills in the Middle East.
So now probably 0.8.
Yeah, so that's what a lot of new steel installations in Central Europe are going towards. They're buying a green DRI plant, which can run on natural gas and hydrogen. They're saying, okay, we're going to start with natural gas, and we're going to later on get the electrolyzer and do the hydrogen thing. So that's definitely a step, right? Then there is that question of can you charge? Is there going to be levels of premium?
Premium.
Because is it the same?
I would ask you, do they then still call it green steel?
Well, it's a great question. It has the industry is growing, right? I mean, maybe they would be like kind of green steel, or they'll be level of green steel. Greenish steel. But like it's a hard question. And then there's also the question of, the DRI, is there going to be a different premium if you're using 100% DRI in a product versus, much less? And these are the kind of questions that, as a company, we're helping the industry define, because there is no standard, because no one's done it. So I don't have the answer.
Right. You have one more question.
Green steel and original steel are the same end products, but only goes through different manufacturing process with reducing. How will you therefore convince buyers to pay more for green steel? What we already have is the bottom line. So we don't have to do it. Because a lot of suppliers want to decarbonize. They've committed publicly to huge decarbonisation targets to help reach net zero as a company or whatever, and then they can slap a big green sticker on their products and say that's decarbonized. Especially when you're looking at premium products, things like electric vehicles. People who are already spending more for their green Mercedes-Benz don't mind paying a little bit more, so that the kind of carbon footprint of their machine is much less. So it's that kind of end of product. Obviously, it's going to be both on the market. And one is going to be, it's going to be do you want to pay a little bit more and get the green product? You already see today, right? When you're buying a flight or something, you can pay a little bit more on your ticket to get, carbon offset of your emissions when you're flying. It's a similar kind of concept. But the bottom line is the demand is there, and we have already demonstrated it's there. There's a massive demand and lack of supply. So yeah, we don't have to.
Let me ask you one last question from me. It's a small island climate change question. So climate justice is a huge issue for us. When you have a premium product and you pay more for green, in worlds like developing countries, what you do is end up making sure the developing countries land in non-green, because we can only afford the less. Is your company thinking about some like the inequity that is created? So you end up with those who are already contributing to the problem and becoming more green, while those who really need to move towards that, you're really creating a demand for the non-green and worsening of potential or possibilities to go net zero.
Yeah, I think that's a great question. I guess as a company, I can't speak for the whole company, but I guess my view is, we're looking at it from just, from the scope of the whole world. So if the whole world needs X amount of steel every year, and that is slowly increasing, as long as we are increasing the portion of green steel in the market, and someone is buying that, that is no one's just buying green steel to have it sit there and stare at it. They're buying it to use in their products. So that is replacing a product that would otherwise be made with brown steel. So the total share of steel being used in the world will be, there'll be less brown steel, less emissive steel. So I agree that percentage is going to be increasing of green steel. That is going to be largely, rich countries able to afford it. And, countries, like Jamaica will not be able to buy the green steel initially.
Unless, for example, your company has a policy where developing countries, there is a special pricing mechanism or something. I'm just
No. I've already been asked that.
Social context.
Yeah.
The whole idea of doing climate change is also the equity. So decarbonization has to be equitable across the world.
Yeah.
So even as you do so, it's a great thing. You want to be part of the green steel revolution too.
Yeah.
But if you create this inequity, there are ways that you can offset it.
Yeah.
I'm just urging your company to think about those at the same time.
Absolutely. No, I think that is definitely something that we will have to think about. As we go forward. I guess right now our focus is just producing it full stop and having people take it. But when then there is so much opportunity for increasing uptake around the world, and also spurring on other projects wherever. Yeah.
I mean, maybe.
Promise I'm not answering that.
You were just tagging on to that, maybe it should be in exchange for the amount of carbon emission that you are. It's a directly, you know, proportional to if you're a low emitter, then you should be getting that right to lower the price.
I see.
Right, from every first time,
Right.
you are reducing on all the kind of thing. But that's why
Yeah.
the mechanisms to think through.
But absolutely, and you know, that's where like governmental policy pricing can come into play a little bit as well, because if there's a price on CO2, you know, the price of brown steel is going to be so high that, you know, the step up to green steel is going to be very marginal in comparison to somewhere where there isn't any kind of, you know, policy that's pushing that as well. So I think in the EU, that's something that's only going to increase demand for green product, because it's going to be so expensive to make brown products very soon.
One question, I'm not sure if I heard right, did you say you're focusing on flat sections?
Yeah, flat steel, exactly.
What's the reason for that? And is that just for a certain phase, or will you, in the long run, be looking at like big like rebar,
Yeah.
structural steel?
So the reason is initially when the idea was fostered by our founders was to mainly be catering for the automotive industry, because we saw that initially as the customers who are most interested in buying green steel and paying a premium because of the boom in the EV industry. Obviously, since then, we've seen there is also huge demand in construction. So potentially, who knows, in a future mill, I think, you know, maybe more likely would be, you know, this hydrogen DRI repeating unit generating the green iron, and that green iron can go into existing rebar mills and then make green steel with our green DRI without us having to make the mill. But yeah, so that was really the motivation. But yeah, there's no reason to say that we couldn't go rebar later on. But obviously that requires, you know, from the steel side, a whole, you know, different, you know, expertise. So we'd have to hire the right people to be able to help us there.
Just wondering, can you just use the iron with electrons with hydrogen?
You reduce the iron directly. Yeah. So it really just, you should say that. So that's what Boston Metals do. So Boston Metals is kind of a startup out of MIT, and they're trying to do exactly like that. I think it's called, what do they call it? It's like MOE, I think, metal oxide electrolysis. And basically they I don't know if they melt the iron or dissolve it. I can't remember, but they do exactly what you're saying, where they're just reducing it in an electrolytic cell. The challenge is that, if I remember correctly, well, I mean, they have a lot of funding and they're progressing, and so this may be a future technology. It is just that right now, unfortunately. The technological readiness is nowhere near the level of this, because, you know, as I mentioned, these are all existing technologies that are proven. That's kind of something that's lab scale or kind of a little pilot scale, and taking it to large scale is a challenge. I think one of the challenges they have is a lot of degradation on the electrodes. So you constantly have to replace them out because it's quite a harsh environment. But no, definitely. I mean, I by no means think that this is going to be the technology for the next, you know, 50 years. You know, who knows what can happen. But this is the best technology, you know, right now. And, you know, that's why the industry is moving that way. But who knows? I can't remember. Yeah, I can't remember whether it's the anode or the cathode, which is the challenge. But I mean, yeah, I mean, you're already using expensive. Yeah. Yeah. No, yeah, no, I mean, in terms of efficiency, it's less steps, right? You're cutting to the chase. Yeah, no, absolutely. Completely. Check out Boston Metals. It's a really cool technology. It's a really cool technology. Yeah.
In a list of partners, do you have any academic partners currently? Is there an intention to have academic partners? Now, a pitch for you. And another thing is, have you identified places in your project and you have where with research, and I'm not asking for trade secrets, with research, you can improve that process, maybe with respect to efficiency or otherwise, you know, and maybe part of the plan of to bring on other research partners.
So I think we're probably most inclined to have technical partnerships with, universities close to home. So like, I think, LTU is one in particular, which is Luleå Technical University. So Luleå is very close to Boden, it's like a half-hour car journey. So I think we're looking at, in collaboration with them, setting up a bit of a hydrogen lab facility to look at testing different electrolyzer technologies right now. But it's still early days. But absolutely, I think, in future, the possibilities are, massive in terms of, academic partnerships, because, we want to be the industry leader in, electrolysis, and also in, steel, co-developing these new grades of steel like any other steel mill does. So in future, yes, I guess it's just a bit less of a priority right now, as we just need to build it. Yeah. Oh yeah, and right now, by the way, just I realized I never mentioned. So right now we're doing groundworks. We've done groundworks. We're laying foundations, and we about a month or 2 months ago we started to erect our first steel columns. So we've started to build out the ground, which is quite exciting. But yeah, obviously there's a lot still to do.
With green steel?
Unfortunately not. We haven't, it would have been ideal. We should have looked into time machines before this. That would be ideal. Unfortunately not. We have to use balance. But it's an interesting question though, because there's a lot of emissions obviously in the construction process, and all of the materials used in building a factory that is over 270 hectares. It's a massive plant. Despite this, we're going to be, kind of back of the envelope numbers, with this difference of the 2 tons to the 0.2 tons, we're going to be paying back all of those emissions in, under a year. Just to give you an idea of, magnitude. And yeah, I don't think we haven't said that publicly too much on our website, because obviously to say these, you need to do all the numbers due diligence, but at the back of the envelope, it's well under a year. So just to give you an idea again. But yeah.
Colleagues, let's put our hands together for filming. It's very fun and stimulating discussion, and it's great to see such an undertaking unfolding. And we thank you very much for taking the opportunity to come share it with us. Thank you so much, and on behalf of our university.
Thank you very much. Thank you very much.
In slow motion.
Okay.
Thank you so much. And we have one other quick before we leave. Colleagues online, thank you so much. We're going to invite us all to the front, please. Please, colleagues, and just the one photo up, please, to just put this out on our social media. You can give us a background that you think would be appropriate. And we will just.
Maybe that one.
Please, colleagues, and we thank you so much for joining us. Colleagues online,